Dave Stewart, development engineer, AEM Electronics. He does a lot of the applications. So the Tesla drive board that we did, they did a lot of the development on that. He's also worked with the integration of a lot of our other products. So back to the map switching. So you can now send your son out on map 2 and not worry about him going out and drifting competitions with the car. So and also if it's raining or anything along that, you can bring the torque way down. It also means that your torque curve can be configured as well. So rather than just being a linear 0 to 100%, you can have it ramped in this way, you can have it ramped in this way, however you really want it. And you can also have torque on demand by time. So using the Cobra Jet 1400 that you might have seen here last year, that was here, it's a 1650 horsepower quad motor. It's got 2 of those in it. That is a drag car, and it's an 8-second drag car. The problem again with all this torque is you can annihilate the tires, or if you have traction, you can literally put it on the bar so hard you can break it really hard. So now we can have different maps to choose from, but we can also ramp in torque based on time. So this is a really trick feature. So when he launches, a timer goes and says the car can handle 1,000 foot-pounds of torque right now. And as it goes, it ramps in the torque or ramps out. Steve Huff's car, the 200-mile-an-hour dragster, that has a torque curve that looks like this. And it's all programmed in over time. So we can actually have that programmed in so it's not blowing the tires off mid-track or even at the big end or out of the hole. Nate was involved with a lot of the programming of this with a couple of the other engineers when Ford was doing the development and track testing of that. And it was new to us too, because the amount of torque that you could bring to the table with these things, that the first time they went to launch the car, just if it didn't have bars, it would have been on the rear bumper. So they had to keep on ramping the torque back in, and then looking at the data, and then getting it so it can actually get down the track. So those are a couple of the really cool features that the VCU brings to the table from the tuning side and from the configurability side. The other component is that these VCUs work with several different inverters and motor combinations, including the Tesla driver board that we have. That means that if you have a Hyper 9, or if you have a Cascadia inverter, or if you have a DTI with an MRX combo, all these different combinations out there, this can work with all of those different devices, which is kind of unique, and it still brings all those feature sets to the table. The other components that we have BMS battery management system. We have a keypad I touched on a little bit. This is sort of that doesn't have to be this way, because some people have classic cars that have been converted, so they might want analog switches in, or they might have their own CAN set that they want to use. But in our case, we have this really easy to see. You have your prindle across the top, you have your ignition, and then you have map switching and a couple other switches that you can set up for different feature sets. In addition to that, we have this little unit here, which is probably one of my favorites. It's called the PDU-8. So this is power distribution. So if you're a builder of a car, or someone's building a car for you, or doing a conversion, one of the greatest challenges is wiring. So when you rewire a car that was wired once, and rewiring it to accommodate all those other devices throughout the vehicle and getting power to that, you have this central location where the harness is coming from, and it spiders out through the whole car. Well, wouldn't it be cool if you're doing a conversion to be able to have the power in the location where the power distribution is required? So this unit can literally be these. How many can we run up to? Four. So 4 PDUs, and they're all CAN controlled. So this is basically a power distribution unit for 12 volts for headlights, taillights, pumps, fans, devices like that. So if you have pumps and fans in the back of the car, pumps and fans in the front of the car, contactor boxes in different locations, you can literally say, I have 3 areas of concern where I need power distribution. You take 3 of these, you place them throughout the vehicle. Now you have these little mini sub-harnesses throughout the vehicle. So you don't have an entire vehicle wiring harness. For motorsport, it's absolutely ideal. We're heavily involved in drift and rallycross and forms where the cars are getting thrashed. But that also means that when it gets thrashed on a corner and it takes a corner off the car, they can replace a sub-harness versus the entire vehicle harness with driving the field repair. This is CAN controlled, so that means the only thing going from this to the VCU is 2 wires, which is really cool. The only thing power going to is 1 larger cable, and all the power distribution goes from here. If you don't have a battery management system, if you don't have a VCU looking at all of this information You can have things like you might have seen videos of thermal runaway on a battery pack where it melted down, or a vehicle that's underperforming, or you're destroying a battery in a short period of time because you really don't understand what you can demand of it. And a VCU, not only ours, but a programmable VCU and a properly installed battery management system can give you some information, and this is going to sound a little weird. It will only give you the power that it says it's safe to give. So you can't overcurrent draw the battery pack when something's properly set up. That means that if you say, hey man, I'm having a really good time, I want 100% of the power out of this, I should get 800 horsepower. Well, if the BMS is monitoring every cell in the pack, and there's all sorts of information that's coming up to the VCU, and the VCU says, wait, we're running a little warm, we're down on charge, so things really aren't safe to give you 100% of torque on demand. We can give you 70%. So you don't even know it, but this is all happening behind the scenes. So it's almost like knock control, to a degree in an internal combustion engine. You say, I want more boost, or I want, more RPM, or whatever it might be, but it limits the power, it trims it back. Being that it's can-based was the big appeal. So we started looking at some of the conversion shops around us, and we saw really quickly that a lot of the conversion shops were doing a really beautiful job on the conversion, but the devices, the inverter, or the battery management system, the contactor box, they weren't really able to communicate really well with each other. There was some analog communication, there might have been some CAN communication, but there was no supervisor system like a VCU. One of our engineers has coined this as sort of the adult in the room. So it's looking at everything and communicating with everything, keeping everything in check. At that point, we're looking at what these conversion shops are doing, saying, there might be an opportunity here for us to bring a control system, in ECU. This is almost like I've used this analogy before. I was an early guy in the 80s doing tuning, and we're using all these little devices like sub-injector systems and knock control boxes and separate boost controller, all these different devices, and then trying to make them work all together, hence the term tuning, so the vehicle performed and stayed together. The conversion shops 5 years ago, when we were looking at that, 4 years ago, looking at them, they were doing stuff very, very similar, making things work together, but there was no supervisor system, looking at everything, making sure that everything's playing safe and happy together, and that's where the VCU came in. So that's really the main role of the VCU. When I say it's sort of like an ECU, but it's more, because it's looking at so much information and properly set up, it brings a lot of safety to it and a lot of control to it. Circling back to the battery pack being a massive investment, or the largest part of the investment for the EV conversion, the BMS, I want to bring Nate in and sort of talk about what is a BMS? I've used the term, it's sort of like, think of filling an ice tray, and it's making sure that all the cells are getting filled up, equally. Not one's higher, one's lower than the other, so it's trying to keep everything equal. But there's a lot more to that. So Nate, just come up.
Who's heard of a BMS? Yeah, kind of, right. So name out something you think you know that a BMS does. What does BMS do? Balance cells, right? So that's one of the first things everyone thinks of, like, we're going to balance cells. So what does balancing cells mean? So just like Kirk's example, you've got your ice cube tray, right? And what we're doing is, there can be, in some cases, multiple thousands of battery cells inside your battery pack, like a Tesla Model S. There's over 7,000, a little bit larger than AA size batteries inside the car, and 16 different modules distributed throughout the car. And so all those batteries, I like to think of lithium-ion battery cells as like your grandma. Like, you want to treat your grandma really nice. Like, you want to keep her happy and keep her warm and comfy, and make sure she's in a tip-top shape and a good mood, because everyone needs to treat their grandma really nice. So the same thing with lithium-ion battery cells. It's just like your grandma. You want to treat them nice and make them happy. So lithium-ion battery cells like to operate within a certain voltage, just like your grandma. She doesn't like to be too hot, doesn't like to be too cold. Same thing with lithium ions. Lithium-ion batteries like to operate within a certain battery voltage, and it's not very big. It's a really small window. When you charge up a lithium-ion battery, it goes up to a little over 4 volts, and it discharges down to about 3 volts. So your operational voltage window is like 1 volt. So you're going to take a fully topped up battery, and so think about a car battery for a moment. A car battery is 12 to 14 volts. And you know that if you're not actively using an alternator to charge it up, it's going to go from 12 volts down to 11 volts, down to 10, 9, 8. It's going to have a pretty wide range of actual usable voltage. When you get into lithium ions, it's a completely different type of battery, a different type of cell architecture, and the live voltage range is really actually very small. So it only goes from a little over 4 volts to maybe down to about 3 or high 2s. So you're talking about maybe 1.5 volts of actual usable range. So in something like a Tesla Model S, you've got that AA size battery, and obviously the car is not going to operate on 4 volts. So how do you turn 4 volts into 400 volts? You take all those cells and you start stacking them up in series, and the voltage starts adding up. So you've got 4 volts, and then you put another one on top of that, now you've got 8. And after you've put 96 of them in series, now you're operating in the 360 to 400 volt range, okay? So now you've got your fully charged up battery, and the individual little AA size battery cells don't themselves have a lot of current capacity. A Tesla large drive unit from a Model S can draw over 1,000 amps, wide open, making all the torque and power it can make. The base drive unit does 1,000, the performance drive unit does 1,300 amps. So you're talking about using a AA size battery cell that's going to power something that draws enough to weld like inch thick steel with. So we're talking about a massive amount of current. So the way you take that battery and make it be able to support 1,000 amps worth of current is you start paralleling them up. So you put a whole bunch of them together, and this battery might only be able to do 2 amps of discharge, but then as you put 76 of them in parallel, that multiplies that up to a much bigger number. And then the discharge characteristics are very short term. So you get a lot of acceleration in the Model S for a shortish period of time, maybe 10, 15, 30 seconds, and then the battery needs to be replenished. So back to keeping lithium-ion cells happy, they can't be overcharged. So you're going to go up to a little over 4 volts, maybe 4.1, 4.2. You can't take a lithium ion to like 4.3, 4.5. They will start getting unhappy. Same thing on the discharge. You can't overly discharge a lithium ion cell either. So going down on the low end, there is a cutoff voltage. We can't let the voltage drop below this amount, otherwise the battery will get unhappy. And unhappy batteries result in bad things like swelling. The battery packs will bulge, and then they'll burst, and then you'll get fumage, which will catch on fire, and we've all seen those videos, and that's the last thing we want, right? So it all comes back to keeping grandma happy. So we don't want to overly charge the battery, we don't want to overly discharge the battery, and we don't want the battery to get too hot, and we don't want the battery to get too cold. So not only is voltage a concern, but how much current we have going in or out of the battery also is very important. So on the discharge side, when you're pedal on the floor, trying to accelerate as fast as you can, and your Tesla large drive unit is drawing over 1,000 amps, the battery, depending on its state of charge, how much energy is in the battery at that one moment, will determine how long you can draw 1,000 amps out of it. So if you're fully charged up at 100% state of charge, you can do multiple blasts in a row and get a lot of current. But then as you start wearing it down, it's like your bank account. Like if you start running out of money, you can't keep writing big checks, right? So eventually you're going to reach the bottom, and you got to like, okay, can't write any more checks. Same thing with the battery. As it runs down, you got to start slowing things down, and instead of 1,000 amps, we're going to do 900, and instead of 900, we're going to do 800. And then if you get really close, you can actually take that all the way down to like, okay, now we're just crawling. So you're gonna get 100 amps just so you can crawl up the side of the road and call AAA to get a tow. On our car, like we'll discharge over 1,000 amps, but then we only allow 200 amps to go back in. So we want to make sure that same thing is as you move more energy in and out of the pack, the resistance that it's working against is going to generate heat. So as you're using the battery more and exercising it, it's just making more heat. The batteries actually do like to run warmish, but they don't like to get hot. So you can run, and I unfortunately operate in metric units, so we do a lot of Celsius. So normal day outside, it's probably 25, 30 C. You can run a battery up to 40 C, they're really happy. Once you get into like 45, 50 C, it's starting to warm up, and then past 50 C, it's like, okay, now we need to start making grandma happy, turn the AC on. And now imagine you've got your fuel tank pickup, instead of being at the very bottom of the fuel tank, is like up an inch, right? So that last maybe half gallon of gas can't go into the pickup to go to your fuel pump. It's the same thing when you run into a discharge problem with the battery. Is if you get so low that, okay, well I gotta protect the whole entire pack. When there's one cell that's too low, I have to stop what I'm doing And whatever little bit of energy was left, I can no longer use because of one cell, right? So it's kind of, you're not making full use of your available power and energy in your battery. You get into things like active thermal management, battery heaters, battery chillers, just like instead of being in Minnesota, you could be in Arizona, where it's like 110 degrees out and you're trying to draw 1,000 amps out of your battery and it's heating, just imagine grandma sweating, just being all mad and just upset. And you're like, no, grandma, be happy, we're gonna cool you off. There's chillers, there's actually air conditioning that gets plumbed into the battery cooling system. And you can wick away all of that additional heat that the battery is generating and keep the battery happy, like grandma. What kind of safety stuff did you have in mind? Prior to a product like the VCU, where the VCU is like the top tier, the top of the totem, and everything kind of architecturally falls in underneath it and is control of it, I like to think of the older builds, which were effective, but they were kind of like controlled chaos. You have these different systems that are kind of clashing. You've got a BMS that wants to do contactor control, and you've got some kind of motor controller that doesn't communicate with the BMS really. All the BMS can do is if you get too low, it's going to open contactors. So instead of derating, which would be a more nicer way of throttling down, instead of just like you saying you're done, you can't drive the vehicle because like your state of charge is too low. That's the kind of functionality you would get when you have kind of this splintered system where they're not working. Everyone's favorite word is there's less synergy, right? So you've got all these kind of fragmented systems that don't really harmonize well together. But then you have something like a VCU, and it brings it all together and makes it work much more easily. So if you're familiar with lithium balance BMS, you're familiar with an Orion, they have these things where it's like, okay, state of charge is too low, open the contactors. Battery temperature is getting high, open the contactors. Because that's literally the only thing those BMSs can do, because the only thing they interface with are contactors. So that would be the same thing as like, ow, I cut my finger, I need to go to the emergency room and have surgery. Like, it's a bit of a dramatic response. Like, you don't have to go to the emergency room to have surgery. If you cut your finger, you just need a Band-Aid, right? So same thing with our system. So instead of being like, okay guys, we're getting low state of charge, open the contactors, we're gonna do like, okay, well actually, why don't we just chill out a little bit and just bring the torque limit down, or do this or do that. So there's more finessing of the system instead of just a brute force like we've got to stop now. So that's what that brings. So inverters in themselves are actually pretty complex pieces of machinery, I like to use the analogy of like a carburetor versus fuel injection. Like AEM, our background is engine management systems, EFI, we've been doing that stuff for 2 decades. You can take a carburetor, like you can take Holley carburetor as an example, and Holley carburetor out of a box will work on an engine that's an inline 6 200-inch to a 350 V8 to a 600 cubic inch with watt Chevy. That one carburetor, because all it's doing is just dumping gas into an intake manifold, and as long as you've got a couple times spark, your engine's going to run, right? It'll start, it will run, and it'll probably drive on just one carburetor, right? It may not start great, it may not drive well, it may not get good fuel economy, it may not do all these things, it may pop and burp and not run nice, but it will run the engine. That is the equivalent to how that control system works. It's like an open source board where it's like a kind of a build your own solder together type kit. It uses a very rudimentary type of control where it's like, well, I'm just going to put a little current here and a little current there, and that's going to make the motor spin, and that's good enough. So that's the type of control you get. You get kind of a carburetor-esque type control with this other system where at the deepest level, the most control you can have is called field-oriented control. And what that's doing is it's actually, there's a lot of, we all know that the electric motors work with essentially opposing magnetic fields, right? So there is a magnetic field applying a repelling force against the rotor, and that's going to push the rotor away. And then when it gets to a certain point, now we're going to pull the rotor, and that whole operation is going on inside the motor over and over and over, many thousands of times a second. So the higher end inverters do that, and they monitor it at every degree of rotation in the rotor. So it's very precise, it's very controlled, and it's very equatable to like a perfectly well-tuned, just perfect running EFI system. We're able to capitalize on that. So we're actually able to realize that additional power. We can put a little more current into the inverter, drive the motor a little bit harder, and make more power. So we actually are able to make a performance gain with our controls, with our Tesla large drive units over stock. When you pair the drive unit with a more performance-oriented battery, additional benefits are realized. the battery is still like by far the limiting factor to performance with inverter and motors. And it's all a matter of discharge, amps, and basically current capacity, like how much can your battery really push through an inverter and through a motor.